afternoon, everyone. As just been introduced, I'm Xueling, a postdoc from Virginia Tech, and also a scientific visitor here hosted by Dr. Wenbing Wang. So I will be staying. Can everyone hear me? Really? Okay, so I will be staying here at least towards next summer. So this is, in fact, not the first time I gave a talk here. I still remember about back to 4 years ago where I'm visiting Art and Tomoko here, and during lunchtime before my presentation, someone scared me here. Like some people here will give me a hard time during my presentation. So as a first year PhD student, I was so nervous then. I can hardly remember anyone give me a hard time, but I was so nervous I just broke the pointing sticks on my hand. So this time, with just this pointer on my hand, I don't think I will break it. Okay, let's back to today's presentation. So today I'm going to share with you about the work I have been conducting on ionospheric ultra-low frequency waves and their geospace impact. So here's the outline for today. So I will firstly introduce some background materials, then followed by one statistical study and 2 case studies. Then I will summarize my result and discuss about ideas for future work. Firstly, I will introduce what ULF waves are. So ultra-low frequency waves, they're essentially MHD waves in the frequency range of about 1 megahertz to a few hertz. So this frequency range spans from the lowest frequency the whole magnetospheric cavity can support towards a few non-zero frequencies. So since those frequencies are much lower than the plasma oscillating frequency, they can be described by MHD theory. So in the cold plasma assumption with a uniform background magnetic field, only the RV mode and the fast mode exist. Here it shows their dispersion relation. So as can be seen from here, the RV wave, they propagate along magnetic field lines, and with a magnetic oscillating component perpendicular to the ambient magnetic field. So they carry no pressure perturbation. For the fast mode wave, they propagate isotropically with the oscillating component parallel to the background magnetic field. Thus, it causes plasma pressure variation. That's also why it's also called a compression mode wave. So these are 2 basic MHD wave mode or ULF wave mode. Next, let's move to some historical background of ULF wave. So ULF wave is more of a modern name. It's back to about a few decades ago, but historically, even a few centuries ago, they were named micro pulsations or geomagnetic pulsations being observed on the ground. So the first record can date back to about 1960s, being measured in the compass measurement. Here shows one example in a compass needle. So this package of pulsations are signatures for ULF wave or geomagnetic pulsations here. Like it's after about 1 century when Danji proposed that using MHD theory that these non-periodic pulsations might be standing RV wave on the geomagnetic field lines. And in 1916, his theory being confirmed with ground encounters where a spacecraft measurement. And since then, ULF wave have been identified being detectable in various instruments, including radars, optical images, and GPS. Okay, so there are a lot of terminology associated with ULF wave pulsations. So to not confuse you, so I will really briefly introduce about different subclasses of ULF wave pulsations. So you may hear about PC5 or PI2 very often. So those are 2 main categories of the pulsations. One is pulsation continuous, one is pulsation irregular. So here's an example of a PC5 position continuous. As you can see, like this position continuous means the waves lasting for more than a few wave cycles and without significant damping of the wave amplitude. But for the irregular positions, they are more impulsive and only lasted for a few wave cycles and then quickly damped out. And also according to different frequency range or period range, they can be further divided into PC1 to PC5 and PI1 to PI2 as shown in this table. So in our presentation, we're basically focused on the PC3 to PC5 and the PI2 positions due to the limitation of the instrument time resolution. And next, I'm going to introduce about two well-known standing wave modes in the Earth's magnetosphere. So one is the phase and resonance, just proposed by Dante about a standing urban wave excited on geomagnetic field lines. It's similar with like the oscillation on a stretched guitar, except that the string here are geomagnetic field lines. So on this dipole geometry of the Earth's magnetic field, so according to different oscillating component, one is like the geomagnetic field oscillating radially inward and outward. So that corresponds to the poloidal urban wave. So the oscillating magnetic field is in the radial component and the electric field in the azimuthal component. While if the geomagnetic field oscillation is in the azimuthal direction, the oscillating like the east-westward direction, that's called the toroidal urban wave mode. So associated with the azimuthal magnetic field oscillation as well as the radial electric field oscillations. So this also being the standing wave, urban wave, being called the phase and resonance. And the second category is called, we call so-called cavity mode or waveguide mode, where we're regarding the whole magnetosphere or like the plasma sphere as a cavity. When there's some energy source kind of strike the whole cavity, it's like striking a bear, then the whole cavity starts to oscillate in its own frequency. So that's called the cavity mode being shown here.
With the poloidal and toroidal alpine waves, what you showed is what would be measured above the ionosphere. Is that also what would be measured at the ground?
No.
Okay.
So it will be measured, but the component is different. Since those waves, they will pass through the ionosphere according to the swing of the ionosphere or the rotation. So the component will be different. Like for here, it's a radial component. It's called poloidal mode, but when it's measured by ground magnetometer, it's in fact the azimuthal, the east-west component. That's called the poloidal mode because of the 90-degree shift of the ionosphere effect. And since we are going to statistically investigate the driving mechanism and the occurrence statistically of ionospheral wave, so it's good to do some literature review of previous studies. So two driving sources associated with the magnetospheric ULF wave. So one is from, we call the external driving sources, where the energy source come from outside of the plasma field, like from the solar wind or like other magnetic poles or even the magnetic sheets. And the other one is called the internal driving sources, which like the source is coming right inside the magnetic field. It's caused due to local instabilities or wave particle interactions. So here this table summarizes of the ground magnetometer or spacecraft observations of a different category of pulsations at different frequency range and different mode. Compression mode, we just mentioned, the fast wave mode, toroid and poloid, and where they usually located being observed, and the associated source, either is from upstream external driving sources, or it's from localized wave particle interaction or instability sources. It's been summarized here. So I think after knowing enough about ULF waves through my introduction, you might ask the question like, why do we care about it? In fact, this slide is intentionally prepared for one of my out-of-area committee members during my PhD defense. Yeah, he always asks like, why people like me know neither or nothing about space science? Why people like me would care about what your research? So So to answer that question, so prepare for these slides. And my answer to that in two aspects. One is the scientific merit, another one is technological application. So a few examples being shown here. One is that ULF waves play an important role in the energy transport throughout the geospace. So one example is that the KH wave excited on the magnetosphere, they can transport energy inward towards the magnetosphere, and then coupled with waveguide mode, then waveguide mode or compression mode, they can then couple with field and resonance, then energy propagate towards the ionosphere or the ground. So this is one example of that. There are also other scientific applications of ULF wave studies. And the other one from the technology part, that ULF wave can interact with atmospheric particles. Sometimes they can accelerate those electrons to the MEV level, which will cause damage to spacecraft electronics. And also they might affect some atmospheric properties, which may affect the GPS signals as well. And one part which I will present in this presentation is about ULF wave can also drive the geomagnetically induced current GIC, which may damage some infrastructures, including like the pipelines or the power grid. So here's the end of the introduction. Let's move to the first statistical study to investigate the overall occurrence statistics as well as the driving mechanism using the super-down high-time resolution data. So before I move to the result, I just want to introduce the main data set used for this study. It's a super-down high-frequency radars. So this radar network is an international network of more than 13 kind of ground-based high-frequency radars. They're primarily designed to study the atmospheric plasma motion. So I think a lot of people may use the super-down atmospheric convection patterns as either driving your models or to compare with the output of the models here. So this map shows like the field of the radar coverage in the northern hemisphere as well as the southern hemisphere. And this animation here shows how a radar operates. It usually scans azimuthally from one beam towards the end, and with a time resolution about 1 to 2 minutes. As you can see, in this kind of normal mode scan, you can only resolve the wave frequency up to the PC5 frequency range. So you cannot resolve high frequency wave. That's why we proposed to use another spatial mode being shown here. So in this survey paper, we used 7 years of atmospheric backscatter data from the super-down radars. 17 of them are rating in the northern hemisphere as being shown here. And we only use the semis mode counting beam data, which will give you a time resolution of 6 seconds. So now how do we get this kind of 6-second high time resolution data? This animation tells you why. So previously I just showed in normal mode, the radar scan from the first to the last beam. But in this semis mode scan, it will come back to one of the beam called the coming beam, where every other beam, so that this coming beam have a time resolution of 6 seconds. But the sacrifice of the ambient beam, the time resolution of 2 minutes. So we're going to only use this high time resolution beams to do the study, so that we can resolve the ULF wave up to the frequency of the PC3 or PR2 frequency range. And some advantage of the radar observation that it can complement the ground magnetometer observations because it can capture a certain wave mode which screened by the ionosphere. It cannot be detected by ground magnetometers. It also have a kind of enhanced spatial coverage as can be seen from here.
Okay, that's a good question about that. So you're talking about the sweeping across beams, but there's also a range. They call them range gates or something like that. Are all of the range gates queried simultaneously, or are those scanned in time as well?
It's kind of being measured simultaneously at one one beam when you're scanning on one beam.
When you're scanning one beam, and then there are what, like 40 range gates or something along that beam, or
More than that, it depends on the configuration of the radar. Some might get 75, but usually you just get a backscatter from a few range gate here in the middle. Yeah, so the spatial resolution is about 45 kilometers in that direction.
in the range direction.
Yeah, in the range
Oh,
direction.
that's where the 45 kilometers.
Yeah, it's 45 kilometers. It's a spatial.
And that's a 6
resolution.
second. So is it
Yeah.
scanning each range gate every 6 seconds, or what?
Every 3 seconds, the integration time on specific beam.
Okay.
So that's why you come back. You stay on 3 seconds on this beam, then come back 3 seconds on this coming beam. Then you scan on the second beam, then you come back to this again. So that's why it's a 6 seconds.
Got it. Thank you.
Yeah. I think it's very straightforward for you to understand, like the waves in ground magnetometer spacecraft measurement, because it's electric field, magnetic field measurement. You may find it less familiar with like the ULF wave signatures in radar data. So that's why I show you an example, like how the ULF wave signature perform in the superdown data here, and why we need to use a high time resolution data. So as I just mentioned, superdown measure the E cross V plasma drift in the ionosphere. So as the ULF wave they propagate through the ionosphere, the electric field oscillation will also cause through this equation cause the plasma drift velocity oscillation. Thus can cause the ULF wave modulation in the background night scale flow. So here, this is the field of view of the Saskatchewan radar. We're going to show like the counting beam, like range time intensity plot, as well as some normal beam measurement. So for this kind of, you're going to see this a lot of times. So this y-axis is a radial we just mentioned about. It basically means like the distance of the target from the radar site. So each radial is 45 kilometers. Then there are certain ways we can transfer this radial into the geographic location or geomagnetic locations. Here I only show the range gate, and the x-axis is time, and it's color-coded by the Doppler velocity measured by the radar. So here the RTI plot shows in the normal beam, you see some structure here, but it's difficult to see if there's any wave signatures there. But if we take a look at the 6 second counting beam RTI plot, you can see at this band there's red and blue alternating. Those signatures are ULF wave signatures in the RTI plot of the radar. You may see something here, but you're not so sure, you're not that confident that it's wave signature here. But when coming to a high time resolution, you will see it all very obviously. And if you get a scan line over one of the range gate plot the time series, you can see clearly those kind of monochromatic wave signatures over here. So those are ULF wave signatures in superdown radar data. And then we developed some automatic detection algorithm to search through all the 17 radar in the northern hemisphere in the counting beam, and each range gate and each 1 hour, half an hour time intervals using non-scheduled periodic method, so that we can get a statistical study of the wave signatures in the ionosphere. So here it shows the ionospheric backscatter distribution, which also means the observation time of the radar through those 7 years interval. So this map is in the MIT and the magnetic latitude coordinate. So you see kind of a constraint of 3 rings. One is the polar region, it covered most of MIT. One is the high latitude region of the high constraint of occurrence, mostly land side, but extending towards the afternoon a little bit. And then the mid latitude. So this is caused because of the radar. There's 3 radar channels here. One is Poloidal radar, one is high latitude radar, one is the mid latitude radars. So you can regard that as some artificial, because we can only receive certain kind of ionospheric backscatter at a certain range gate. It's not kind of uniform across all the field of view of the radars. but it kind of shows what's the distribution of the ionospheric backscatter. Then, based on this, we search for the wave signature. If at each different local time and magnetic latitude, there's how many wave events be observed there.
You know, given that the radar beams are overlapping, why are there gaps on the left?
Which gaps on the left?
Well, in your distribution, your occurrence distribution, you have gaps between polar high and mid, but radar beams are all overlapping. Why don't they fill in those gaps?
It's just like, for example, for the high latitude radars, it's mostly constrained, like, for example, like 10 to 20 range gauge. So it's always being observed at kind of certain latitude. For the mid latitude radar, it's also similarly kind of being observed here. So even if the field of view, we have a very large field of view, it's not always like everywhere you have observation or backscatter.
Okay.
So you need a certain condition to be made so that you have the ionospheric backscatter back.
Okay.
You can regard this as a limitation of the radar observation here. So here we show the spatial occurrence distribution of the wave. So the first column here is what I just showed about the ionospheric backscatter distribution. Where the first row is for PC3 to 4 pulsations, and this is for PC5 pulsations. And the second column is show the actual wave occurrence in this map. As you can see, like PC3 or 4 wave have a kind of high occurrence out of this region, high latitude, dusk side, and also more wave event being observed on the land side and mid latitude. And here's for the PC5, mostly concentrated in the polar region and the high latitude region. If we divided this kind of wave event by this backscatter occurrence, then we get the wave occurrence probability or the occurrence rate here. It's being shown here. Like a few features from this plot, like the first one is this one I just mentioned, that like the occurrence probability is kind of high on the dusk side of this high latitude region for the PC3 to 4 frequency range event. And another category is this one on the land side or pre-mid land side, like on the mid latitude. And the third category is for the PC5 wave event, which have a very high occurrence probability also around the dusk side, but at high latitude. To note that for this event, the probability, the highest is kind of 12%. Here is 24. So the PC5 occurrence rate is much higher than those of the PC3 to 4 frequency range wave event. And it's just 3 categories, which we will investigate more later. Also, we studied some the seasonal effect of those wave occurrence. So we divided the occurrence probability according to summer equinox and the winter, and found that this category of the night side mid-latitude wave event, it occurs occurrence probability is much higher in the equinox compared with the other 2 seasons. And for the PC5 wave, in the dusk side high latitude, it occurs more during winter times. So I will expand this one later. It has something to do with the night side, like the geomagnetic activity. That's why it occurs high during equinox. And this one, it has something to do with probably to do with the ionospheric conductivity difference between different seasons. And also overall, you can see the polar region PC5 wave. Also the occurrence probability is higher in winter compared with the other 2 seasons. So the ionospheric conduction might play a role in controlling this ionospheric wave occurrence rate. As I mentioned, there are 3 categories. One is the mid-latitude land side PC3 to 4 event. The other one is the dusk side, the PC4, and then is the dusk side PC5 event. So I want to study like if those 3 categories have a different kind of driving, what different driving mechanism or different wave occur at different locations or different frequency range. So I sorted those events by AE indices, symmetric, and FBZ. And it's like probably in probable analysis, but not exactly with that. So the x-axis is the time. So 0 it means the onset time of the event being detected, and then we search for the A indices like a few hours before, a few hours after. For the other two categories, it's kind of 1 day before, 1 day after, because we thought these two categories more associated with the storm intervals, and this more associated with substorm intervals. So let's take a look at that. For these like night side events mentioned, you will see kind of the wave event associated with the elevated geomagnetic activity. That is an increase in the AE indices as well as a decrease in symmetric, and mostly negative would be the IMF. So it's more probably associated with substorm activities. So even though I categorize those as PC3 to 4, in fact, they might be more associated with the PI2 pulsations, which is well known to associated with the substorm activities. And then the second category is the dark sky PC4 event. As you can see, it occurs during the minimum of the AE indices, and there might be some substorm activity going on a few hours before this kind of event. And it occurs during a gradual increase of symmetric indices, and the MF is kind of fluctuating. So we think this kind of category of event is occurred during the recovery phase of magnetic storm, which probably is associated with localized wave particle interactions. And in my next two case study, I will introduce one example from this category, another example from this category, and to confirm that they indeed occurred. This one during the substorm, and this one occurred during the recovery phase, and driven by some localized wave particle interaction process. And this one is kind of a well-known like PC5 wave, probably being observed at the dawn and dusk, and causing by the KH wave, which during northward IMF conditions. So here's a summary of the first statistical study. Like we did a comprehensive survey of the ionosphere ULF wave in the PC3 to 5 frequency range using 7 years of super-down high-time resolution data. And we categorized the wave spatial occurrence frequency characteristics, which I didn't show here, seasoning effect, and their dependence on solar wind geomagnetic conditions. Here are some of the main results being summarized here. I will just let you read it. 3 categories of wave we found, and the suggestions on their driving mechanisms. Then we move to the second study. This one is associated with this category, the dusk side PC4 event observed during the recovery phase. So it's being shown here. And before I show some of the observation or the result, I just want to briefly introduce about the wave particle interaction theory, because we'll discuss about this in the end of this study. So if you still remember in the introduction about the poloidal wave, it's a ULF wave oscillation in the radial magnetic field and the azimuthal electric field. So this azimuthal electric field, if it meets certain conditions, it can align with the particle drift direction so that it interact with the magnetosphere particle, can either accelerate or decelerate the magnetosphere particles. So here it shows we call that in wave particle interaction the drift bounce resonance condition. Here's the wave equation shows this condition. So for example, for the fundamental poloidal wave, which is being shown here, here's the structure of the magnetic field. Here's the azimuthal electric field. So they can interact with with the ions. If the ions always sitting here, which is the positive azimuthal electric field, so it can receive net acceleration, then be accelerated by the wave. And here it shows how the second harmonic poloidal wave geometry of the electric field, magnetic field shown here, how it can also interact with the westward propagating protons and also being accelerated or decelerated according to where it sees the electric field.
So the waves themselves do not have any significant longitude modification.
this you see this m value, it suggests the kind of propagation of waves in the azimuth direction. The waves that also propagate, the particle also propagate. So as long as they meet certain conditions, like in the rest frame of the wave propagation, you will see particles always sitting somewhere.
These are standing waves on the magnetic field?
It's standing on the magnetic field now, but propagate azimuthally.
It's a radial wave oscillating in and out.
Yeah, yes, like this.
And the D and the B refer to drift and bounce?
Yes, this is drift velocity of the particle. This is bounce velocity of particle. And here's the wave frequency and the wave azimuth propagation wave number. So as long as they meet these conditions, they'll be able to meet this drift bounce resonance condition for the wave and the particle to interact. Okay, so when the wave particle they in interaction, like it can like in both ways, like energy from wave to particle or energy from particle to waves, depending on like this equation. Since we are studying the wave generation, so we are more focused on like the free energy from the particles, which can drive the waves. So it will be made by this equation shown here. Like so there's two mechanisms can provide free energy for the wave generation. One is like the bump-on-tail particle distribution, where you have a positive slope in the phase space density of distribution with the energy of the particles. So this kind of free energy of the particles from this bump, they can provide. Of course, they have to meet the wave particle interaction condition first. Then it will generate the wave. And the second is like through this mechanism, where the distribution of the particles have a radial gradient being shown here. So in this study, we're going to show kind of one long-lasting poloidal wave, and to categorize the spatial extent and provide evidence of how the waves being excited through this wave-particle interaction. So here is the event overview. As I just mentioned, this event being observed during the recovery phase of a modern geomagnetic storm. Here it be shown the symmetric indices here. This assigned shaded region indicates a wave being observed by the two ghost satellites. And here is almost 10 days. So it's during the later recovery phase of storm. And here's the 3 days zoom in of this interval of the AE indices. As you can see, the wave being observed during kind of very quiet AE indices. But right before the wave onset, you see a large substorm going on. The AE indices reach about 100,000 nanotesla. So this is all consistent with the statistical study. And we're going to use the ghost and semi-satellite in the magnetosphere as well as a ground-based instrument like 3 super-down radars operating in this high-time resolution mode to investigate this wave-driving mechanism. So let's first take a look at the wave property in the magnetosphere from the ghost satellite. There are two ghost satellites, ghost 13 and ghost 15. So the geosynchronous satellite, and we show like the time series as well as the dynamic FFT from 3 different components. Here's the radial component, which suggests a poloidal mode, and here's the azimuthal component, suggests the toroidal mode. This is a compression mode, and so for this dynamic FFT plot, the y-axis is frequency, x-axis is time, so that you can see how the wave power changes with time, as well as the frequency changes with time as well. So first feature is that the wave are very monochromatic, so it's almost centered about 5 to 10 millihertz by both satellites being observed. So these concentrations, and since the wave power is strongest in the radial magnetic field, so we call it the poloidal mode dominant ULF wave. And also, so this red line suggests noon. So as long as the satellite moves towards the day side, you always observe those kind of waves, even though the frequency are decreasing and their spatial extent are also shrink with time as well. So this is our 3 days of measurement. So as you can see, like the waves been sitting there for almost 3 days. The whole day side is all oscillating in that poloidal mode wave. So this is the interesting of this event. And then let's take a look at the wave signatures in the ionosphere from the Superdown radar. So here's the RTI plot we showed before. As you can see, this very weak reddish and yellowish alternating stripes, and then it's become the bluish and the reddish, also oscillating stripes are signatures of ULF waves. So if we take a look at a certain range gap, you will see like the wave amplitude is about 100 or less at the beginning. And then it got intensified towards 300 meters per second at this time interval. And if we do a FFT analysis, you can see the wave is pretty monochromatic also between 5 to 10 millihertz, which is consistent with the ghost satellite measurement here. And if we take a look at all the observations from all three radars, the frequency change with magnetic latitude, you can see a clearly kind of decreasing frequency with magnetic latitude, which are signatures of the phase line resonance, because at a high latitude you will have a lower frequency range because the length of the phase line becomes longer. And these are just a few features from the radar measurement here. And if we put the space and the ground-based together in a map showing all the events being observed by the 3 Superdown radars with triangle, cross and plus being shown here, and 2 ghost satellites, which are diamond and square being shown here, you can see they're pretty consistent. The frequency are pretty consistent. All being observed mostly during the day side. And so the azimuthal extent, that means the azimuthal extent is pretty large, but they are focused on about 65 to 70 degrees out of the subaurora region. And then we also investigate, as just been introduced, the driver of those kind of waves through the CEMIS satellite measurement. CEMIS also measure this monochromatic wave in the azimuthal electric field component. If we take a look at the iron-phase space density distribution, the function of the energies, you will see that a small bump over here, and it gradually disappears as the satellite moves away from the wave active region. Because the CEMIS satellite is in eclipse orbit, GOES is always kind of in the same area here, so that's why GOES always observe those waves. But CEMIS, when it's in eclipse, and it will pass through the wave active region very fast. So through this kind of analysis, we suggest that this wave was generated by this kind of bump on tail and distribution at a few keV energy range of the ions. And also through this kind of wave particle interaction process, you can estimate the wave azimuthal propagation number, which is the M number. It as high as minus negative 200 in this case. So here's the summary of the second study, which is the first case study here. A very long-lasting poloidal wave, which being identified as the second harmonic phase line resonance being observed, and multiple satellites as well as multiple Superdown radars operating in the high time resolution mode during the recovery phase of a geomagnetic storm. And the waves have a very extended spatial extent in the day side azimuthal direction, but it's localized at a certain radial extent, which could be as localized as just a few hundred kilometers in the ionosphere. And the source of the wave is suggested to be the bump on tail distribution and through a drift bounce resonance with particles in the magnetosphere. Okay, here's the second case study, which we are going to categorize the geoelectric field associated with a kind of ULF wave, which we call a plasmaspheric virtual resonance. So just a little bit of background about ULF wave and the GICs, or geoelectric field, just in case. Because this project just started this summer, so even I am not that familiar with like the link between ULF wave and geoelectric field. So as a ULF wave, they can generate the geomagnetic perturbation on the ground, and that geomagnetic propagation can then drive the geoelectric field, or GIC, through this equation here. And the geoelectric field is a very fundamental parameter being used to model or predict the GIC. So that's why we're interested in how different ULF waves they can under different conditions they can drive different kind of GICs on the ground. And in order to get the geoelectric field, it can either be directly measured. So there's certain stations which can measure the geoelectric field, and it can also be estimated if you have the geomagnetic field perturbation, as well as this kind of impedance tensor being shown here. This impedance tensor depends on the Earth's electric conductivity. So it's the combination of the wave amplitude or properties, as well as the localized Earth's conductivity, which determines the amplitude or the polarization of the geoelectric field or GIC being generated. So that's why the study of ULF waves is also important for this study. So at least a few past studies focusing on the link between ULF wave and geoelectric field. So even though there are a few studies here, and the fact that ULF wave being studied for more than a century, there's still very limited papers or investigation trying to focus on the ULF wave as a driver of the geoelectric field or GICs. So that's why we proposed in this study to using a coordinated space and ground measurement, trying to address the science question of how do ULF wave in the MI system coupled with the geoelectric field that's related to the GICs on the ground. So you can find more details of this event in this paper, which will confirm that from the satellite as well as the ground magnetometer and the sweep-down radar measurement that it's a PI2 event, which is the first category of event we just introduced in the survey paper associated with the substorm onset at a period about 17 seconds, and it's a standing fast mode wave. You can find more about that details in the paper. But in this presentation, we're more to focus on the geoelectric field associated with this planetary virtual resonance. So showing on this time series are observations from the two summits satellite, one outside of the plasma field, one inside of the electric field measurement, as well as through three ground magnetometer in the magnetic field measurement, and then one of the shoot-down radars, as well as 3 stations over here have the direct geoelectric field measurement. As you can see, they all observe, except for the first one, because it's the virtual resonance. This one does not observe the actual pulsation, but it observes something else. So let's focus on these few panels. So the PI2 pulsations on the onset of that are pretty simultaneous across all these instruments, satellite, ground magnetometer, radar, as well as the direct measurement of geoelectric field. So this is, as you can see, these 3 stations have direct geoelectric field measurement, even though they're pretty close, and their geomagnetic field should be, which is the black line, you might find it difficult to see, pretty much similar or the same in the polarization as well as the amplitude. But the geoelectric field oscillations are quite different across these 3 stations. So this is similar with the Bestdraw and Love 2015 paper, except they're using a uniform magnetic field perturbations and try to model the geoelectric field across the US stations. But we use the actual event, ULF wave event, and also we find similar conclusions that it can vary because of the 3D Earth's conductivity are different. So here, just showing for one of the stations, the time series of the measured magnetic field, horizontal magnetic field, as well as the measured geoelectric field. And also, as we mentioned before, the geoelectric field can be measured as well as can be calculated if we have a geomagnetic field, as well as the impedance tensor from the MT survey data here. So as we can see, at least in the PI2 frequency range, the estimated as well as the measured geoelectric field are pretty consistent with each other. That means this kind of the empirical impedance tensor get from the MT survey is very reliable at this location, at this event. So we can use this to do more work. But let's first take a look at like this 4 dashed line here to see how the geoelectric field evolved with time. So here it shows 4 different time intervals, and at this region, we just show there are 3 stations have the geomagnetic field, geoelectric field measurement. But in fact, there are more than that. There are about 10 stations here. They are pretty close located here, and the black vector shows the geomagnetic field measurement at different time intervals. As you can see, at each time interval, the geomagnetic field, their polarization as well as the amplitude are pretty similar because they are very close with each other. But the geoelectric field response are very different. Like the amplitude here is pretty large, and at this time interval, and this time interval, this one is pretty small, and then the polarization also change during the next time interval of these stations. So this is just to confirm that even if, like for this event, the geomagnetic field perturbation are quite similar, like because it's a cavity mode, so across all kind of the US stations, the magnetic field polarization and amplitude are very similar, but the geoelectric field response could be very different, and that's mostly due to the effect of 3D Earth conductivity structures, which are being shown here, like those color-coded dots shows the resistivity, which is the inverse of the Earth's conductivity, which is also where this is the impedance depending on. So I'm not an expert on how to explain like why like across these stations like there could be different Earth conductivity. That has something to do with the geology, kind of the property of the rocks, or like the anyway, I'm not an expert, so my collaborator from the USGS, they might be able to help like explain why the response might be different. But my job is trying to derive the geoelectric field associated with this different kind of wave mode here. So here's just a very preliminary result showing like how the geoelectric field could be associated with ULF wave. So since there's very few kind of studies trying to link these 2 phenomena, and we seem to be the first one to explore the relationship, and using the platzspheric virtual resonance as a case studies, and definitely more work are needed to explore the relationship between the ULF waves as well as the GIC or geoelectric field here. So that's all of the 3 studies. Here's a brief summary. I just need to read just a statistical study, a long-lasting poloidal wave case study, and a geoelectric field event associated with the ULF wave. And some implications from these kind of research findings. Firstly, like through the statistical study, I think it provides a very good constraint on where, when, and how often we observe ionospheric PC3 to 4 ULF wave. This might be useful in the future when people want to do modeling or want to know where at different latitude or MLT, what kind of waves are more often being observed, and what is the occurrence rate being associated with that. And for the non-lasting poloidal wave, even I didn't investigate that in my case study, but a few recent studies showing that they can contribute to up to 85% of increase of the DST star indices during the recovery phase of magnetic storm. So it's an important kind of factor of the energy loss of the ring current protons during the storm time. And also some previous study also showing that the total energy deposition in the ionosphere associated with ULF waves is also not neglectable. That's also something I'd like to do while here in HAO. And as just being shown, like ULF wave can link with the GICs, and large amplitude wave can drive probably large ground DBDTs, while those kind of smaller amplitude but have a large scale but long-lasting wave, they are potential drivers of the GIC that could cause the pipeline corrosions. So these are just a few geospace impact associated with different kind of ULF waves. So one of interesting future work, or the work I'm working right now, I just want to draw your attention. And maybe if you're interested, you can also join for this project. As I just mentioned, like this kind of Gauss-Superdown conjunctions of this long-lasting wave. I just did one case study. And this paper coming out almost simultaneous with my long-lasting paper last year. They use a very interesting method called sonification, and using citizen science with high school student in UK. They're trying to also identify exactly the same kind of wave event, long-lasting decreasing polar field and resonance following a geomagnetic storm. So through this kind of method, we may be able to find. In fact, in their study, they through kind of a search of 1 year of ghost data, they found more than 20 events. Because mostly associated with geomagnetic storm, it depends on the occurrence of geomagnetic storm as well. So this event is not as rare as we thought. So it could be occur pretty often. So we want to study more about this kind of event, and just to show you how you can listen to ULF wave in space. So this is kind of pretty much the cycle of a storm. Like you at the main phase, probably like you have a kind of crunch sound, and then followed by this kind of poloidal mode, decreasing frequency. So they speed up like the satellite record, the ghost satellite record, like of a whole year of data to probably a few minutes. So then you through certain kind of software called Audacity. Even I'm just learning how to use that. So you can listen to, that's pretty good kind of guide or structure on this website you can find. You can download almost 9 or 10 years of ghost satellite data, and then train yourself through according to the guide, and then to see if you can find this kind of wave. And then there's a Google, there's a spreadsheet over there that you can record, like what is the wave frequency, what is the start of a wave, and what is the duration of a wave. And you will find enough wave events, then we can do more statistical study of this kind of event, and which I think is very interesting. If anyone of you are interested in getting involved, please let me know. Or you can just go to this website to find more information, or contact Martin directly. Yeah. And here's just more ideas which I'm going to work here. So if you are interested, like modeling or kind of categorizing the geoheating associated with ULF wave, we can talk more afterwards, since I will be here towards the next summer. So whenever you feel like. That's all I have for today's presentation. Thank you for your attention. Okay, yeah.
I have a question about the second study.
Uh-huh.
And in particular, that one plot of the data you showed where every time GOES would come around in the day side,
Yes.
the magnetosphere of the ULF waves was not
Mm-hmm.
this one. And yet the interpretation is a wave-particle interaction for stimulating it. But it's natural to wonder, if the solar wind is variable and it's banging up against the magnetopause, why wouldn't that stimulate waves on the day side like these? So why is that not possible?
I think for the solar wind driven waves, that might be mostly in the compressional mode, and you need to have a consistent kind of driving always being there. And I didn't find a particular kind of solar wind driver for this event. And since it's a very high M number poloidal wave, it's very unlikely to be driven by external sources, because the solar wind driver is always have anti-sunwater propagation, and their properties and distribution might be a little bit different from this kind of.
I understand. I didn't appreciate these were high mode.
Uh-huh.
What's the upper?
It's about minus 200 something. Yeah. But that's through the wave particle interaction kind of equation. We assume it's caused by that, and do the calculation. And there's also a few kind of similar studies. I have a table in this paper summarize that, and it's mostly being attributed to localized wave particle interaction, and it mostly have a very high M number. And also I checked the ground magnetometers nearby. They cannot resolve these waves. So those highly not be screened by the ionosphere. Only radar and the spacecraft can observe them.
What's creating the free energy source of the particle?
That's something we need further investigation. I cannot give you a kind of the correct answer at this point. I think that needs more investigation. We have some suggestions, but even I doubt that.
Are these superdome radars exclusively used for research?
Yes, you mean for what kind of research or?
Research, or do they have other functions or other uses?
Yeah, I think it's mostly just provide data product of the plasmaspheric, the drift. I think it's mostly for the scientific research. It's not.
I gather that there is no data exchange with Russia. Is that
There's no superdome in Russia. They don't want to play.
Yeah, you take a look at the gap of. There are radar there, in fact. I saw papers, there are radar, similar radar there, but they're not part of superdome, or they do not call their superdome, or, yeah, that's Russia. So the gap here, which caused some of the, that's Russia, yeah. I don't think we have any military kind of research. I think it's more about NSF kind of grant, kind of just science.
Your conclusion about the loss of energy of the ring current
Uh-huh.
particles, I'm not sure if I
Yeah,
did it
uh-huh.
quite fast, and it was surprising to me.
Uh-huh.
So if I understood what you're
Okay.
saying is that a good fraction of the loss of energy of ring current
Uh-huh.
goes into generation of
Waves.
ULF waves.
Yes.
So it's not a question of pitch angle scattering of ions that they just get dumped into the ion.
No, it's just those ring current at a specific energy range. They provide free energy to waves. So this energy transfer between like the ring current energy. So we think that during the recovery phase, like you see the DST can gradually increase. That might have something to do with like this kind of ring current proton energy loss.
Does that apply to the entire range or
A specific range. Yeah, I think that has specific frequency range, energy range. Like for my event, I thought it's a few keV, like protons play a role. But in other studies, when it's kind of different wave particle interaction condition being made, it might add a higher, like tens of keV or even 100 to 100 keV protons as well. So it really depends on like the wave frequency, like the particle frequencies and the M number as well.
Say you want to estimate how
Yeah, Juhi.
ULF wave affects
Uh-huh.
so you are predicting from down ULF wave from the Backscatter.
Yes.
Excluded from estimating ion. So how exactly you plan to do that? What is the amplitude of that?
It varies. It could vary from tens of meters per second to a few hundred meters per second. Like I did some calculation for the second study, when it's about 300 meters per second, which is the largest amplitude, it corresponds to about 15 millivolts per meter electric field. And if we do some calculation with the assumption like the wave spatial extent and the wave duration, the total energy could be kind of large, even though the localized geoheating rate is small, but the total energy depositing into the ionosphere could be large. So at least for this specific event. So.
Because I don't know the details how you extract
Uh-huh.
the magnitude, because that's
Yeah.
So from the Backscatter power intensity versus the Doppler shift versus the regular effluent,
Uh-huh.
which you use to estimate that, how the difference is?
You mean the wave amplitude as well as the
The velocity itself. You said it's 300 meters.
yeah.
Which is quite large in terms of, regular, normal signal point.
Yeah, usually when I do this,
Usually
usually I will when I'm finding those wave events, I do detraining, I will subtract those kind of background, so that you can, so that's already being there might be a large background electric field as there as well, and then overlay on that as the amplitude of a wave.
Just say, if you just do sinusoidal, 300 meters
Uh-huh.
amplitude wave on the regular
Uh-huh.
convection velocity, is that how you plan to do, or?
I haven't thought about how to do that. But I just kind of roughly estimate that. Yeah, that is something I'm still kind of in my mind trying to propose something so that can do some more work about in that aspect. Thank you anyway. Any more questions? Okay, thank you.